And that was a challenge of ours because not being able to check the box, so to speak, of like having 10 gigabit was challenging, right? Like some people just wouldn't talk to us because of that.
Welcome to the LabVIEW experiment. I am your host, Sam Taggart from SAS Workshops. In my 15 years of working with and training developers, I've had the opportunity to conduct a lot of experiments. Over here, we believe in embracing failure as the essential learning experience that it is. And what better way to learn than from other people's mistakes? In this podcast, I talk to industry experts, colleagues, and friends about their failures and how they have turned them into future successes. I am here today with Terry Stratoudakis of ALE Consultants. Some of you may know Terry from his book on FPGA. It is one of the few FPGA books for LabVIEW. So when I say he wrote the book on LabVIEW FPGA, it's because he did. It's pretty much the only one there. And Terry has a very interesting story about how he got started with FPGAs way back maybe a decade ago now with some Wall Street stuff. So I think that's a very interesting story in the LabVIEW world because I don't think many of us equate LabVIEW programming with the Wall Street and financial transactions. So I'm just going to let Terry tell a story because I think it's a really interesting story.
Sure. So I guess living in New York at the time, this was around 2006, 2007. We started to look at like a LabVIEW toolkit, just purely software. And then in 2008, we attended a conference that was called High Performance Computing HPC on Wall Street. And we saw that people were talking about using GPUs, FPGAs, GPS timing on the data centers, like so they can keep all the data centers like synchronized. Just a lot of high tech stuff. And we saw the FPGA part. We saw that people were challenged with like how to program the FPGAs and how to find people that know how to work with them. And the other thing that was also really interesting about the timing of it, right? If you know that September 2008 was like the financial crisis was sort of taking off is not the right word for it, but it was getting underway. And so, there was like a lot of uncertainty as well, but it kind of made us curious to sort of pivot into, well, let's look at the hardware side of this. And so we had heard of LabVIEW FPGA, and we said, that this is something that's high level. It's kind of like the way LabVIEW helps people write software more efficiently. So that's the story that we understood from NI, right? Like that LabVIEW FPGA could do that for FPGAs. And so we started to kind of started to research like feasibility and is there the right hardware for it? Is there, can we build something that's the right performance? And it was we had to understand like what the needs were, and so there were already companies making. So like I guess maybe we can talk about what the problem was that they were solving, and basically it's really like a data center problem. So like you have all these computers that are in the data centers, and if you think of it as a control system, they're receiving data like the sensors in quotes are all kinds of market data. And there's lots of exchanges out there. There's news, there's unstructured data, there's all kinds of information that's out there. And this information is sort of coming into these computers. They're doing all kinds of things to reduce the data or maybe focus in on like what information is important or look for some kind of whatever it is they're looking for. And then there's something that makes a decision and says, okay, buy this, sell that, or a combination of those things. So you think of that's like the full control system, and it's supposed to run, for a certain period of time, like all day, pretty much. And the reason, like the first thing, like for an FPGA, that's sort of like the bigger picture, and then within that they need to do risk checks, right? There's all kinds of like financial things that they need to run. Where the FPGA comes in, if we take like in quotes, the simplest use case was market data. So like for like certain stock exchange, there's like say like 5,000 symbols, like ticker, like stocks that are out, like trading at a given point in time. If a trader is only interested in like say 20 of those or 50 of those at a given point in time, they don't need to have all of that go into their computer and then get filtered out. So they would have these essentially like these appliances that essentially had FPGAs inside of them that would look at the network traffic and do what's called the deep packet inspection. So it would look at the data that's coming in and it'd say, okay, this is for this symbol, we don't care about this, throw this packet out. This is from that symbol, keep it, send it in. And why would they need to use an FPGA? Why wouldn't they just make this like hardwired? And the reason for that is that the exchange protocols, they would have like a protocol that sits on top of UDP or TCP. They would change every couple of months, whether it was based on, there's new information they want to include in there, or maybe there's some kind of regulatory thing. For whatever reason, every couple of months, those protocols would change. And so that's why it had to be in an FPGA. It had to be in something that was, reconfigurable, that could be changed on the fly.
I have a weird technical question for you. So, if you're inspecting the network traffic on the FPGA and filtering it out, how does that work with encryption? Is the FPGA like terminating the SSL connection and then like creating a new SSL connection, or how does that work? Because if the data is encrypted going through, it would be hard to do the deep packet inspection, right?
Yeah, it wouldn't be encrypted, and the protocols
Okay.
are the protocols are published by the
Okay.
exchange. Like it's something that's not I think connecting, and typically the data would come in as UDP, even though we know UDP is not really reliable because it's more or less like a closed network. It
Hmm.
was something, and they would have extra redundancies, like they would actually send out two feeds at the time, so that way you can actually, the first thing you would actually check is that you would see the two feeds coming in, and you would just compare them to make sure that like one isn't dropping, like one is, they're consistent.
Okay, cool.
But yeah, there's a lot of network questions, right? So the problem wasn't necessarily like in that sense. The problem wasn't necessarily financial. The problem really was more like software. What's called like software defined networking or a
Mhm.
smart network card or smart NIC. So that's like one part, right? Where you want to be able to like filter out the right amount of information, get it into someone that wants to make a decision, and then execute an order or send out a trade order, and that they want to do, send that out. Um, the part that we focused on, we kind of like were going to conferences and meeting different people, and it was really really a hot item. It still is a big deal for them. But what was really amazing was that what was exciting, I guess, was my brother and I were partners in this. We would just say, hey, we're working with FPGAs, and we were able to get meetings with, banks, with exchanges. People, was really something else. Of course, at some point, we'd have to explain to them the tools that we're using. And, this is where it's interesting when you talk to someone about the tool you're using versus like what it can do for you,
Hmm.
right? So if we sat down with someone and we started to talk about LabVIEW and LabVIEW FPGA, they started to kind of scratch their heads because they would say, like the other 9 people that we talked to are using VHDL and Verilog and these other approaches, so that kind of made us seem a little too like outliers to them, right? They were kind of like this doesn't really make sense, right? These were business people that, even their technical people didn't know a lot about FPGAs at the time, as opposed to, if you go into like an aerospace company, they know what even the business people know about FPGAs. Whereas at the time, 2008, 2009, in the financial world, like they knew about networks, they knew about software, right? They knew about a lot of other things in technology, but FPGAs, like some of the meetings were just asking us like, what is an FPGA? Or sometimes they would even ask us, how does an FPGA compare to a GPU? Which at a really high level, they're both hardware accelerators, right? They can help accelerate something. But as far as connectivity and connecting to a network or solving problems, the types of problems they can solve certainly have some overlap, but they also are very different in some ways. And so, uh, it was pretty exciting to get all these meetings and, meet different people and kind of learn, what's the purpose of these different things in the market, in finance. Um, what we chose to focus on was two things. One was sort of accelerating calculations, and the specific one was option pricing. So, which option pricing is done with it's a Monte Carlo simulation. One way of doing it. So you try just random values, And the numbers, that was one place where we were able to test to see how efficient was LabVIEW FPGA. And I recall at the time we were able to do something like 800 million or 900 million simulations per second. And when we talked to the GPU people and the other FPGA people, we were pretty much on, pretty much competitive. They were getting similar numbers. And so that was kind of like our first check. I mean, we did a lot of other checks in terms of learning live FPGA. We were learning, say, like the fixed point math and how to process, the single cycle time loop and other things that we had to just learn about. We also did compare it to some of the other tools that were out there, right? Like MATLAB had a HDL coder, and there were some other tools as well that we wanted to sort of evaluate things, take a sort of a bigger picture approach. So once we saw that we can actually make an efficient FPGA, and we sort of understood the technology, we started to look at what kind of hardware we could use. And at the time, there was a company making, so because connectivity was important, we needed to be able to connect to different networks. At the time, I would say probably most computers probably had a 100 megabit. Gigabit was sort of new, but the data centers were using 10 gigabit. And that was a challenge of ours because not being able to check the box, so to speak, of like having 10 gigabit was challenging, right? Like some people just wouldn't talk to us because of that. There was like a FlexRio adapter at the time that was made by a European company that had two 1 gigabit adapters on the FlexRio card.
Mm-hmm.
So like that card just had the PHY chips. So we were getting basically like in the OSI model, there's like this 7 layers. We were getting like layer 2. So it's pretty low level. Like once the electrical conversion happens, we're just getting the bytes.
Mm-hmm.
So it was good enough for a demo. And then what we chose to focus on was in finance, they have various protocols that they use for communications. And one of the protocols that they use is called FIX, which I think is Financial Information Exchange. And it's at the time I kind of thought of it as like, well, maybe this looks like it's GPIB for finance. It's everyone is sort of a lot of people have their own protocols, but that was one protocol. A lot of exchanges and a lot of places had their own protocols, but that was one that was pretty common. And because it was sort of this like open community, we thought this was something that we sort of latched onto that, and we had FIX on an FPGA, and that also got us a lot of meetings. Like people were really interested in that. So in the end, we were able to do. There was one project we were able to do where there was had to do with financial news. The problem in that case was every couple of days there's news that comes from the government that has to do with like inflation data, unemployment data, all kinds of information, and that information gets sent from Washington to whoever's subscribing to that. Now, most people see that information, like on a web page or, not in terms of microseconds. But there are financial firms that pay to have a lower latency connection to that information. And then there's news agencies that will provide that to them. And the project we had was kind of a R&D project to understand how to reduce that latency.
So I have a couple questions.
Sure,
First,
sure.
is the 1 gigabit versus 10 gigabit thing, was that just a limitation of the NI FPGA hardware, or was that just, yeah?
Yeah. At the time, it's funny. Right now, NI has a product line that's called the high-speed serial cards. 65, 91, 92, 3, 4, 5. Like there's a whole bunch of these cards that they came out with. Literally, like we called it quits on the company, and probably 2 years later, and I came out with those cards, and it was I don't know if it would have gone differently if those cards existed.
So that would have been a good sales pitch to help you sell.
It certainly would have been a big changer, and then NI has like today NI has not only that, but NI has 100 gigabit, in some of their products. I mean, it's
Crazy. Yeah. That's
because the people that are doing data captures, the amount of data is so big that you can't just send it to like a PXI controller or a computer. Like you need to be able to like take the data and then just like it comes in, and you need to be able to send it out to like a data center grade like server.
Is that what most data centers are running now? 100 gig?
I mean I don't know what the I think it just it's certainly those are some of the numbers. I'm not too yeah, you hear 40, certainly those are the rates, right? You'll hear 400 in some cases. I
Wow.
think it's really relative. It really depends on like the um I guess there's like junctions and there's
Yeah.
yeah.
Well, some of that is probably based on need too, right? Because you could achieve those high speeds, but it's probably a cost associated with that. And so, I imagine like the price for a 10 gigabit switch versus a 100 gigabit switch is probably pretty high. So if you aren't trying to move that much data, then maybe it's not worth it.
Right, right. I mean, I know for us back then, one of the qualifiers in terms of like who we would look to do business with was they had to be in a data center. Because if you're not in a data center and you're just writing some algorithms that are running on software through like your bank or something like that, the FPGA is like if you're just trading from home, it's not, the FPGA is not going to make a difference because whatever savings you get locally, you're going
Yeah.
to lose it on all the hops, right? So you have to be like you have to be in the data center for them.
That close to the big pipe, I guess.
You need to be close to the pipe. Yeah, to me, it meant that latency mattered to that particular user.
So I have another question about all the government data that you said you're collecting. What were you like? Were you just filtering that data on the FPGA, or were you actually doing any of like the machine learning type algorithms or anything like that, or any
Oh,
data
it
processing?
was another role the FPGA could also do is you can instrument it. So you would use GPS timing to like you'd have like data as it's flowing. You can check to see like how quickly it's moving through it.
Hmm. Okay.
And so in other words, like if I have an FPGA card with a GPS receiver, because GPS gives me time that's synchronized to globally. If I have that set up somewhere and then I have it set up somewhere else, let's say one is in New York and the other one's in Chicago, I can tell you exactly when the packet that I sent over, I can measure that to very high accuracy.
Ah, okay.
That's really as we know, right? The only thing you can't improve something, right? Isn't there a quote that says like you can't improve something unless you measure it, you can't improve it.
Yeah, yeah. You need to,
So
yeah.
really the first step is you need to instrument it. You need to measure like how good or how bad is the latency. So that was that one like it was an actual paid project that we did. A lot of the other stuff was just our own proof of concepts and I think that the sort of tribute to like LabVIEW FPGA was that sometimes people wouldn't even believe that we had built what we had built like in the demos and proof of concepts because they saw just like two people that really we were self-funded, and whereas like a lot of other people had like VCs and big funding and we were able to build this stuff very quickly because we didn't have to make our own hardware, we didn't have to write like a lot of low level code, and we were able to kind of focus on the application.
Yeah, that sounds like a great application for LabVIEW. I have a couple other questions. So just a random question about FPGAs, right? One of the big things in FPGAs is because it's kind of hardware, you can do stuff in parallel because you don't have like everything funneling through like one CPU. Were you able to take advantage of that on this project? Do you have like multiple connections coming in, or how did that work?
On that project, we didn't so much have parallelism, but with when we did the Monte Carlo simulations, there you can run massively parallel. I mean, we had like one core that would run, say, at like 100 megahertz, and then we were able to fit 8 or 9 of those. So now we're able to run instead of we're running at 100 megahertz, we're now running is that times 8 or times 9. So you can run more of those. But when we were doing the latency measurement, it really wasn't about the parallelism. It's really just we're able to just measure something. It's really just taking a measurement.
Okay, other quick question. Speaking of speed and stuff, uh, were you using PXI based FPGAs or the Cerio based ones? Because my understanding from talking to you is there's kind of a difference in how you use those two things, right?
Mainly PXI.
Okay.
Yeah. There's less layers and less you're you're able to just achieve higher performance with the PXI or PXI Express now.
And then were you,
Stereo, yeah.
oh, my next question then was, well, finish your thought first, actually.
I think Stereo is more for like reliability for like control systems. Like if you're on an oil rig or a manufacturing plant, you need to have that like uptime and that sort of environmental ability. Whereas like PXI tends to be, more like lab grade. I'm generalizing, of course, but that's typically where I'll see it.
Okay. And then my next question then is like for so the controller part, were you using real time or was it just a Windows-based system or did that matter? Or were you
We
just
were
like,
just using Windows.
okay,
Yeah, because we had all the critical stuff was being done at the FPGA level, and so which is an important part when you architect any of those systems, right? You'll see people putting, it's common not just in finance but even in test and measurement. People will say, well, let's put everything on the FPGA, but really carries a very high cost and risk of having all that in the FPGA that we really don't need to.
okay, so like maybe like a configuration interface or something was on the Windows side, but then once you downloaded all the important bits were running on the FPGA and maybe some like
Yeah,
reporting or something on the other end or something like
right,
that.
right. In fact, these days, like when I work with any FPGA project, I try to, even if they've made the decision to go with FPGAs and whatever it is they're doing, I really do try to qualify that they really do need to use an FPGA. Because if you're just using an FPGA just for the sake of it, there's no number to put to it. But like your costs, your risk, your maintenance, your cost of a change,
Yeah.
all these things really just like pile up. It's not just like sometimes a design decision could like make some downstream costs. With an FPGA, those things are just all magnified.
Yeah, definitely. We'll talk about that once I have a short story, just like I worked at this company and we had a project and we had a C-RIO just
Hmm.
because they wanted to be able to say that it was a real-time system. And we
Okay.
didn't do any real-time stuff at all. Like we just wrote it like it was a Windows thing and ran it on the C-RIO. We didn't even bother like measuring jitter or any of that stuff or like, and so it's just
Yeah.
kind of funny. But to your point though, that just made it take longer to recompile stuff and download stuff and run stuff. And I'm assuming FPGAs take a while still to compile.
Yes. Yes. That's always going to be, well, not always, but the FPGAs have gotten bigger, right? Like maybe they've gotten better at the way the compiles run, but the FPGAs themselves have, the size of FPGAs is really in line with like Moore's law. Like whatever improvements you see in the semiconductor world for CPUs and GPUs, the FPGAs are right along. They're inheriting all those benefits of the semiconductor world. They're semiconductors, really. That's
So question then, has its whole compile time gone up or stayed steady? Or like, because you've got two variables, right? The FPGA gets bigger, which takes longer to compile, and then, but compilers have gotten better at the same time. And like, yeah,
I
have
think
they,
it's the compile times have gotten bigger,
oh,
longer.
because
In
you're
my
just you're trying to put more stuff on there and cram it, no matter how much
those
fast.
chips are getting bigger and bigger,
Yeah.
and you know,
Okay.
I would say that our compile times started out maybe like in the tens of minutes, and I've had compiles that you have to run them overnight or like literally like 15 hours on the high end, on the extreme side. I mean that's sort of like with any FPGA project, the elephant in the room is the compile time. And the thing is, it's not really compiling, right? It's synthesis. Other things, there's things that are happening, right? With compile, like we think in the software world, we think of it as it's turning it into machine code, right? It's like linking, it's doing there's a whole bunch of these software processes that are happening. Whereas with an FPGA, I think the term is like it's like an NP complete, or it's a very complex problem, and it could go down a certain path, because it is trying to like fit an algorithm to like the hardware is fixed, right? So it has some algorithm that has to then first synthesize, and then it has to place it and route it, and then meet timing, right? So there's a whole bunch of things that are happening that you can do a whole bunch of things, and then at not the last minute, but at stage 3 of 5, it realizes this won't fit. or it fits, but it can't meet timing.
So it's kind of an optimization problem then, kind of like a linear programming kind of optimization thing.
It's I think the complexity of what's going on in the compile is beyond me. It's
Okay.
really
But when it goes down that path and it's okay, I've laid it out, now I'm going to try to make it fit and it can't fit, does it just fail or does it go back and try again and try something else then?
it does try things. It does try different things. It also there's different seeds, so that way like each compile is not going to be identical. So like some compiles, like if you think of it as a circuit and you've got a bunch of components, if I gave you a bunch of components on the breadboard, you could make the same circuit many different ways if the circuit were simpler. But as the circuit gets more complex, there's probably just, if I gave it to you or to anybody else, right? There's one way we're making that circuit.
So,
And now, yeah,
I was gonna say I have a question though about the seeds. Does it spit out the seeds it used at the end when it's successful? So then you can
it
recompile that same build with the same settings?
so on the LabVIEW FPGA side, that there's things that they kind of hide from us, right? They don't you don't get to set on the LabVIEW FPGA side, you don't get to set that. But if you were working with the, like Xilinx's product, was Xilinx is now owned by AMD. I still keep saying Xilinx, but if you're using Vivado, which is their IDE and their compile tool, you do get to control that.
And can you use Vivado then directly with the LabVIEW FPGA stuff or
Some of the NI products have something that's called the Vivado export. So
okay.
you can take your whole LabVIEW FPGA project and you export it and you make a Vivado, essentially like the Vivado project, right? It's an ID, it's really an IDE, right? So when you're in that, you get more control over what you're doing, and you can also see more results. Like
Okay.
I know we worked on projects when the compiler results we were getting on the LabVIEW side, LabVIEW FPGA side, were just, by design, right? You're not getting a lot of information as to why it's failing. And one of the tips we got from NI was to export to Vivado, run the compile, and then now we can see a little bit more detail, a lot more detail.
Yeah.
And you can even see how it's trying to lay it out. I mean, you can see a lot of things on the Vivado side.
Yeah, my question about the seeds was kind of like, I guess if you build it in LabVIEW, then and it actually compiles and stuff, you better save that bit file because you might not be able to recreate that exact bit file, right? So like if
That
somebody gave me a project and they just had the source code and they didn't have the original bit file, I couldn't necessarily recreate it.
there's different, right? There's different ways that people follow, like as far as process. For our projects, we're saving code and always saving like when a bit file is made, certainly as not just because of that, but certainly like let's say it does take 20 hours to make that bit
Yeah,
file. In those worst cases, you don't want that person to have that burden of having to rebuild that, right? Like in other cases, maybe a rebuild isn't that big of a deal. But certainly in our process, we do keep the bit file is part of like we keep that together.
yeah, definitely. Yeah, I mean, I know for a lot of my LabVIEW code, like, I mean, I do archive the exes and stuff, but I always have this like thought that I can always go back and rebuild it if I need to.
Right, right.
Um, but actually, thinking about that, I'm not entirely sure that that's like binary compatible either. I think I've been told it's not. Like if
It
you run
it
the
may
build
it may not be right. I mean, that's a
later,
yeah.
you may not get the same bit for bit executable. So
Right.
even if you run it on the same machine, right? Like obviously, if you build it on a different machine, then the dependencies might be different or something, or it might have a different CPU and optimized differently or something.
Yeah. With FPGAs, there are some designs. If the design is, I don't know how to say it in a more technical way, but if it's a more full design, you actually may get like a partial pass. Like you may not get like 100% pass rate.
Ah,
So you actually have to send out, and you have to run it like multiple times, and then one of those will pass. And if that passes, the quality of the tools, the compile tools, these, the more modern tools, like I'm told that 15 years ago, that wasn't the case. Like even if you had a bit file made or a bit stream made, you still had to go and check it. But right these days, if you get a compile, like a successful compile from the LabVIEW FPGA side, you that's considered it's considered good. I mean, we still have to chat test it.
I was gonna say,
um,
yeah, we'll touch on testing some more a little later.
yeah,
Definitely
yeah,
a conversation. One of the last questions I have about this part though is you mentioned data centers. I'm curious
yeah.
of the timing. Were they like physical data centers or were you doing AWS stuff at that point in
No,
time?
These were physical data centers.
Because
You know,
yeah,
because
UPS probably doesn't have a way to rent FPGA stuff, and probably certainly not LabVIEW FPGA, right?
well, it's funny you mentioned that. Like AWS does have something called an F1. I've never used it, but AWS does have something called an F1 instance, which means that you're essentially renting time on FPGA hardware.
Ah, but
Like
you
you're,
probably have to do it with VHDL, right? Because they probably don't have the LabVIEW.
yeah, yeah. I don't know which tools they give you, but it's if you go on there, like you'd have to check to see like which I'm not I don't recall like which one they're using these days. But it's yeah, you're essentially like renting time on a couple of FPGAs.
I guess in theory, right? If they had the correct FPGA, you could potentially write it in LabVIEW and export it. Would that work?
Yeah, so NI does have something. They came a couple of years ago. They came out with a LabVIEW FPGA IP export.
Okay.
So you could take your LabVIEW FPGA code and then export not all of it. You're only supposed to export like the algorithm part because
Hmm.
if you export the parts that are like the FIFOs and the outside interfacing, that's not going to be the same, right? Like even if it's the same chip, that's I think the qualifier is like it has to be the same product, like same family.
Okay.
So it doesn't have to be the same exact like model number of like FPGA. If it's the same family, you can export that out to what's called like a netlist or VHDL, and you can export that, and then that can get integrated into the other card.
Cool.
Although I think that features exists. One of the reasons it exists is also for like inspection. So like some places want to be able to inspect the VHDL that LabVIEW FPGA generates.
Okay. So they're not necessarily using it for anything other than just
They could,
and
yeah, you could, but that's um, one of the reasons they would want to use it, right? Like it's one of these places where they want to be able to inspect the code.
is that something where like maybe you would want to use that with like Git so that you have like that net list and you can see what changed? Because I'm assuming diffing LabVIEW FPGA code is just like diffing normal LabVIEW code. It's
Yeah,
less than desirable.
yeah, it's yeah. I mean, the other thing that I would say is that typically for the same size of a project, it's hard to make these equivalencies. But if it's like a 6 month project of LabVIEW code, LabVIEW only, versus like a 6 month project of LabVIEW FPGA, typically the amount of code that gets generated is a lot less on the LabVIEW FPGA side. So you could even like inspect it yourself, like the LabVIEW FPGA code, right? It's not like whereas like 6 months of development in LabVIEW, you could have thousands of VIs, and it's
Now,
more code can be made in that same period of time.
is that because, so one of the questions I have is like the compile time and stuff has to lead to really long feedback cycles. Is that why it takes so long? Because you just have to wait for it to compile and check stuff. Does that change the way you work? Is there a way to get faster feedback?
Well, yeah. So um, I guess the one thing that we'll do is simulation is one thing that we'll use heavily to get that feedback. So, like, let's say there's like a specific algorithm you want to put on an FPGA. It's not just advised. It's a best practice. The people outside the LabVIEW FPGA world use it all the time, right? They don't write anything without simulating it. And so, although in the LabVIEW FPGA world, I have seen some developers skip the simulation step, which I think is a risk, right? It's kind of can be a big risk. But simulation, generally taking a step back, simulation is what allows you to see, you can, for example, you don't want to have to wait like hours for a compile to run, and then you realize that you just wired to like a subtract incorrectly, like something that simple, or like as far as the bitness of the integers or the fixed point math, you've configured it incorrectly,
Overflow.
and you just get like it just saturates, or it goes to zeros, or it goes to some like max value because you didn't do that right.
So what are the limits on the simulation? I imagine it's something like timing probably is one of the limits. Like you can't verify timing.
Yeah, you're not, well, with simulation you're trying to really just check the behavior of it.
Okay.
So if I put these values in, some timing, there is some clock aspect to it. So in other words, like the simulator is aware of like the fact that there's cycles. So when I send like data into the simulator, simulated like code that's running simulated, it knows that this data came in on clock, cycle 0, then cycle 1. So there is elements of like handshaking. Like there are things that are not so much. Um, there are elements of timing, but the way LabVIEW FPGA does it, we're focused more on the behavior of it.
Cool.
Although in the Vivado world, they are checking at timing as well. They are doing they can output that data into, and I guess on the LabVIEW FPGA side, we will output the data to make the equivalent of like a logic analyzer, right? So we can kind of see when this is true, this is false, and you can kind of get a sense of like how it's actually going to operate. And it's
Now, oh,
you can the any simulation, right? Taking a step back
yeah,
isn't perfect, but the idea is that you want to squeeze as much out of the simulation capability as possible,
yeah,
right? Because if you're not like that, the cost of doing that, like so, for example, in LabVIEW FPGA, we have peer-to-peer, right? It's the ability to go to stream data from one FPGA card over the backplane to another. But peer-to-peer doesn't simulate. So the idea there is that you need to just kind of like make your codes that you figure out, like assuming that peer-to-peer is going to work, since it's been in LabVIEW FPGA for a long time. We assume that that part's going to work. Maybe we make a separate unit test for that to just assume that that part's going to, just going to kind of confirm it. But we just kind of like we break our unit tests along those lines. Like the parts that don't simulate will either like we'll exclude that from the simulation, so that we at least we can just test out those parts or simulate them. The simulation is a test, right? So it's
yeah.
we simulate those as much as we can.
Yeah, that was gonna be my next question, actually. So for unit testing, are you running unit tests on the FPGA? Are you compiling the FPGA code and then running unit tests on the LabVIEW side afterwards, or both, or how does that work?
Both.
Okay.
That depends on the project, right? So you know, I've talked about like projects where there's like multi-hour compiles, but there are some products that NI makes where the compile time is minutes,
Okay.
and in that case, you could just run the bit file, right? There may be. I'm not saying that you would bypass that, but you could. The cost of that of getting to that hardware test is a lot lower, or the threshold to it. I think I would say I would add another factor to that. Um, Another benefit of simulation mode is that I don't need to have the hardware, right? Like a lot of times I hear people starting a LabVIEW FPGA project and they say, well, I can't start because I don't have the hardware. And that really shouldn't be the problem, right? Like, because you can load LabVIEW FPGA and the driver, all that stuff. You can pretty much see the whole environment without hardware. And so if you're stuck, if you can only test on hardware, that becomes a big limiting factor. I mean, if the hardware is out for repair, or if it's out in use somewhere, or if it's in, and now you get like a request for a change, I can't validate that change until I have hardware, right? So you want to be able to like verify as much of that as possible, or at least get kind of a warm and fuzzy that that change, uh, what the impact is.
Yeah. No, we're
So
definitely
there's
gonna.
a lot of other reasons, not just because of like a 5 minute compile, you would think, well, we don't need to simulate. But it's there's other reasons I think as well.
Yeah, I think we're gonna talk about some of those in a minute, but I have another kind of
Yeah.
question that you sparked earlier, so we're kind of gonna jump around a little bit, but we'll get back to the testing part. Um, when we talked about AWS, do you want to talk a little bit about AWS and using virtual machines for
Yeah.
development purposes? Because you are one of the few people I know who actually does. I mean, most people I know use virtual machines, but you're one of the few that actually uses AWS. So
Yeah. Um, I I guess the more general thing, right? Like commonality that we all have. I think what's really happening in not just the LabVIEW world, but in general, right, is virtualization. So I think that's I'm a big proponent of that. Certainly, which one we use, right? Like that's everyone makes their own specific choice. But I know when I first started to use LabVIEW, even before the LabVIEW FPGA days, right, we'd have multiple versions of LabVIEW,
yep.
multiple toolkits, and multiple and especially working as a consultant, which version do you put on there? Do you pick the biggest customer? Do you pick the customer that's calling you the most? Like, how do you choose what's going to be on your computer?
Yeah, and then you install a new one and it breaks all the old ones. That was the thing. And then
Yeah,
like basically the only way to fix some of that stuff was like wipe everything and start over again. And then like the order really mattered. And it was pretty
Yeah.
crazy times.
So to me, I think that you know any kind of virtualization, I think is I'm a fan of because it should, especially if you're handling multiple projects with multiple customers, you know, like so to me, like using virtual machines, right? I did play around with some local virtual machines,
Hmm.
and you know, we did our own review of, you know, it's kind of like a buy versus build, and you know, for us, kind of our thinking was, you know, we're not an IT company, right? We're our focus is LabVIEW FPGA, and consulting customers. And I know you can buy servers, you know, like we found like aftermarket servers that we could buy and set up in our office. Um, but then, you know, we just evaluated both, right? And so for us, it landed on AWS. And the thinking is that, you know, AWS is very, you know, very featured. They have, you know, you can kind of spin up different VMs. If you have people that aren't like all in the same location, like here, we're kind of our team is on across a couple of states on the East Coast here. They can all access it. If they're accessing a virtual machine, you know, they like in the past, if I had someone working with me, I'd have to make sure that their computer was configured correctly, or you know, and all these headaches. Whereas now, like they're connecting into this, I would set up their machine, we'd image it and say, okay, you know, this is what you're working on for this project, and that's it. That's what they were using,
Is it easy
and
to just copy it and create another one for another team member then? Pretty
yeah,
simple. Yeah,
yeah.
exactly.
If we needed, or if it got messed up, so, you know, somehow if it did get messed up, you know, some of these had to have a lot of things configured on there. And then the other thing that I also liked was that it also like compartmentalized all of our customers, right? So that way I would connect into that computer, and it only had files from that customer. It only had, you know, configs. Whatever was on there was just from that customer. It didn't really mix things from them.
So
And
if for
then
some reason you wanted to give a customer access to that, you couldn't, it wouldn't be a big deal because they're not going
we
to.
could we haven't had a use case for that yet, but we sure could. You know, that's yeah.
So along the lines of VMs and spinning stuff up, do you use that at all for any kind of CI stuff? Or are you doing any kind of continuous
We
integration or automation stuff?
we did configure a CI/CD for LabVIEW FPGA.
Okay.
Uh, we've used it on a couple of projects. It's sort of it's a capability that we have, right? Like that we've built out so that way it does like the most basic check is like the compile check. The other thing would be just, you know, each of the simulations. You could run the simulations, and that's another thing. You can run those in the VMs, right? Because the simulation doesn't require hardware. We can run them in the VM, and just it gives us results that it all passed.
Is it pretty easy to do that then programmatically? It's just like running normal LabVIEW code programmatically.
For the most part, NI has a folder called there's an RVI folder. It's in like the vi.lib. I know that like isn't there like the hidden nuggets or something like
Yeah.
that? Is that not
Yeah.
Darren? I think made that like presentation, right? The hidden. So there is one of those hidden things is a folder called RVI, and that does have some things that allow you to automate FPGA compiles.
Okay, cool. That might make a good presentation for something like GDEFCON and A in nudge. It's cool. Um, Great. Do you mention any of that in your book? We should talk about your book a little bit, right?
Yeah. Which
Uh,
I
I,
certainly
is that tip in your book? I honestly I read your book, but it was a while ago, and I don't do enough FPGA stuff that most of it went over my head because it goes into a lot of detail about certain things, and I was just like, that's very interesting to know if I ever need to know it. I know where to look.
yeah
But
it's certainly we talk about I believe at the time we were using, I'm trying to think of like when it was written, and you know, because it's been 2 3 years now. um I know virtualization is a topic, so I know that we do talk about that in there. I want to say that we were kind of at the cusp of like starting to use AWS. um Certainly we do talk like simulation is simulation compile times is a big topic, right? That's always been a topic.
yeah.
Um, but at whatever level of virtualization, you know, it's we definitely do talk about that in there.
So one of the other things I wanted to talk about, and you kind of hit on it a little bit, I think in our conversation earlier, you called it systems engineering, but kind of this idea of test-driven development and testing and doing things incrementally. And I think you and I worked on a project together with some people doing some FPGA LiDAR stuff. And what I found interesting about that was like their test process was literally turn the thing on and wave your hand in front of it. And if you can see your hand on the screen, then it's working. And I, I I tried to get them to do some more testing and I was not very successful. But then once you came along, you're just like, we're not doing anything till we get some testing done. And I thought that was really good. I liked your approach. So do you want to talk a little bit about that?
Yeah, I guess I guess there's a big cost to that, right? Like if you don't have a way to test something, right? Especially in that project, we had some stuff that was already written and existing, and someone says, okay, well, this isn't working, and now we want you to get it to work.
Hmm.
So, right, isn't that sounds like a test, right? Or at least multiple tests, or they would say, hey, if I go and do this, this doesn't work. That
Yeah.
sounds like that sounds like a test, right? So certainly, that's it's almost inherent like to anything we do, and it's I think when you consult with someone for you're doing this for a while, it's you reach a point where you know that like your effectiveness in working with someone is not even diminished. It's just it goes to zero, right? Like or negative, right? Like it's almost like the deal breakers, right? Like there are certain things where like it's I know when I first started doing consulting, like you couldn't imagine like you kind of want to do all the work you could find, right? But at some point you realize that there's test and I guess in our world, right, with the FPGAs, the long compile times, we have all these already built-in risks or built-in factors. And I know in that project there was no simulation. There was no way to run that. You may recall, right? There was no way to run that without the hardware. So the
Yeah.
only way that it could run was we had to be remoted or connected to that computer, and we had to run it on hardware, and maybe with someone doing a bunch of things in front of that, right? Like waving something or doing something to it. So I mean, think about the cost of a change, right? Like I go in and make one little change. Now I have to go and I have to either like go there physically or get someone from over there to test that out. So it's that's a big cost. I think another thing they had was multiple cards. And in their case, there was no way to run it with just one card or to run like a simpler version of it. Everything was, the FPGA code, the host code. It was very, we had to really kind of break it up into pieces. I think in the systems engineering world, they call that it's decomposing it, right? Like you have like the bigger problem and you sort of like break it down. And certainly other paradigms may have other terms. But that's one thing that I think we've really settled on, like a very consistent approach, is a systems engineering approach.
Yeah, you definitely helped tame the chaos in that project because it was kind of chaos and I was trying to like wrangle everything and I was not really succeeding. And I don't know, like, but maybe it was just you came in from the outside and you were just like, this is crazy. We're gonna stop this.
Sometimes a fresh set of eyes. Like,
Yeah.
yeah, yeah. I mean,
Yeah.
it's
Yeah, maybe it was like the fact that now there's two people telling them that this is kind of crazy.
yeah,
So, yeah.
yeah. Sometimes the dynamic, people need to hear it multiple times, right? It could be.
Yeah.
It's
The,
hard to say what the factors are with those projects.
yeah, the other interesting point though, I think is too, often I inherit stuff like that where there are no tests and stuff. And I think like as soon as you find a bug that you go to fix, like the very first thing I think, and Fabiola preaches this too, I think it's a great idea, is like write a test to catch the bug at least, right? Even if you're not going
Right.
to test everything else, just say, hey, this does this thing. Can we write some code that will fail, but when we fix that, because like at some point, if you fix a bug, you have to know that the bug's fixed before you say, yes, I fixed it, right?
Yeah,
You don't
yeah,
really like prematurely jump out and say, yeah, I fixed it. And then they run it. No, no, it's still doing the same thing. You
right.
want to at least be able to say, well, I fixed it on my computer at least. Like, let's figure out what's different with your computer or something. But
Or the settings that it works under, because like you may test it out with certain settings or certain values that you're inputting, but then when they go to run it on their end, they're putting other values,
yeah,
and the same code is the test is failing. So to me, that's like you have the tests and we have cases, right? Like you have like
Yeah.
you write out like all your tests, but then like what are all the cases that you're gonna like test with?
Well, that's one thing I see teams struggle with too, actually. So one is like not testing or not having that like to me, it's almost like this mental model of like how you make changes. Like you have to have a way to verify it first before you go make the change. But
Hmm.
the other thing I see people making mistakes with is configuration and not managing configuration very well. Quite often, like it'll run on this computer, but not that one because the configuration files are completely different, and like they haven't given any thought to how to manage that.
Well, that's I think that's where the VMs help, right? Because we know that this VM was built very specifically, right? Like we knew that we know that we installed all these things, right? And that is being managed, right? Like it's very strict. I think even before automating like the build of that, right? It's good to just document all that, right? To know exactly what files and what software is installed on that machine.
Well, you're hitting actually a different level. So I was just talking about like configuration files that that the LabVIEW code reads in to configure stuff.
Okay. Oh, yeah, yeah, yeah. Right.
So
Like INI files and
which is so there's actually like three levels to this really. There's the like configuration files that your code reads in directly that you're writing and you're creating. There is the configuration like NI max and that type of stuff.
yeah,
And then even higher level, there's the drivers, the version of LabVIEW, the version of Windows.
yeah,
Yeah. And
yeah. It's a
yeah.
yeah. Sorry, go on. Yeah.
Well, I was gonna say, I feel like one of the hallmarks of somebody who I would consider like a more advanced programmer, more advanced systems designer, is they take into account all of those things, all of those that configuration, all those dependencies. I think, you know, the naive approach is to just say, well, it works on my computer, so it'll work everywhere. And yeah.
Yeah. Yeah. I'm trying to think. There was a case recently where it was working on our computers and it wasn't working on theirs, and we had to really untangle. We had to find that difference, right? Like I think we had taken for granted that everything was the same, and then we had to, keep stepping back and check firmware of hardware and the, sort of back to basics kind of thing, right? Like, we thought we had everything consistent, but yet it was still we were observing that kind of a difference, right? And we thought we had it all, right? But you know,
Yeah, that's definitely something too. Like when you add an FPGA, right, you're adding that extra level of configure, right? I assume if you add an FPGA card, there's possibly some configuration of the FPGA card itself, and then there's also the bit file that's running on it. Do you have any tips or tricks or best practices for managing all of that?
I think that when you're working on an FPGA project, you're building an instrument. You're building like you're making hardware.
Mhm.
And if you think about like I don't think this happens as often as it should, but like if you go and use something like NI DAC cards, you see that there's like a DAC card and then there's DACMX, right? There's this API that allows you to control the card and do various things. And you don't need to know how it was built, right? Because a lot of DAC cards do have FPGAs in them, right? Like they're FPGAs in a lot of places. They're just not user programmable. So now when we go and build, an FPGA based system, it's important to create a good API for that FPGA bit file.
Mhm.
So, I don't think it's not so common to combine these two things, but on NI's website, they have this thing, this section, the driver network, instrument driver network, right? Where you can download all the different drivers. So there they have like a template for how, if you're writing a driver from scratch, right? Like a Visa driver or GPIB, they say like, these are the types of functions you should have. You should have an open and a close and configure and data functions and status and reset, like all these like really high level common types of functions. Well, I think that if you're making an FPGA bit file, the like if I just give someone like the bit file, that's really not going to be very useful. Really, that bit file is supposed to come with, it's almost like a DAC card, right? It should come with like the bit file, but it should also come with some a good API, like a good library that's written it's in LabVIEW, or if it's if they're going to use it in C or whatever the language is. But let's just assume they're using a LabVIEW host, LabVIEW, and then like some example code that exercises that, or we can call them tests. Maybe it's not exhaustive, but at least it's able to execute it in the way that it should run. And those VIs, that API that you make for the bit file, should be something that a user can understand, right? I don't need to have you don't want to push because it's complexity, right? Like if I'm encapsulating that in complexity in the driver, then the person who's going to use the bit file that I made with the API that I wrote doesn't have to understand all the complexity that's going in there, going on the FPGA, right? They're using it just as another instrument, right? They're opening, they're closing, they're configuring it, they're doing things that they would do with any other instrument. So I would say that that's a so a lot of times people don't connect those dots of LabVIEW FPGA or FPGA development and then what you do with like making an instrument driver, right? Because like I'm sure we've all made like instrument drivers for like cameras or for like motion controllers and different things. You'll follow a certain template, but I think that should be applied also when you're making a host interface for an FPGA card.
Yeah, I actually really
Pyro,
like that approach. I thought what you did with that project that we worked on together, definitely, I thought that was a
they
good.
didn't have an API, right? Like
I haven't.
the
They
host code, yeah.
kind
Sorry,
of wrapping. They had a DQMH module kind of wrapping the FPGA code, but yeah, it definitely needed a more of an API.
they got to really wrap those, right? Like
Busy and doing stuff, and yeah, I feel like in that case, like the thing to do was to create the API like you did and use the DQMH just for the messaging to send stuff back and forth to it and interact with the rest of the program. And that was a much cleaner design.
yeah,
Yeah.
yeah. I would also say that there's been projects where, in that project they had two cards, and the way that code was written, they could only run two cards and only two cards. They could never run just one card. So that means that if one card was broken, the system is down.
Hmm.
If they needed to add three cards or four cards, it's almost like re-architecting.
Yeah.
Whereas if it's written as an API for one card, I've worked on projects where we went from one card to two to four to eight cards, and that sort of takes care of itself, right? Because it's been written to handle that one card. It's all encapsulated in that driver.
Yeah. No. So typically if you have a multi-card system, you just write the driver for one card and then in the calling software kind of chains them together somehow. Is that
If
generally?
they're Well, I mean, think how would you handle if you had a DAC card,
Yeah.
and you had one and then now you had eight, the DAC API can handle that.
Yeah, the calling system then handles all the complexity of managing the multiples and coordinating. Yeah.
Now, sometimes we may need to write some extra functions for synchronizing them.
I was going to
So
say
like,
the synchronization is the thing that I would think might change. Yeah.
yeah, yeah. So we have to like that's kind of an abstraction thing, right? Like where we need to see like, do we put that in the driver or do we write that like just one layer on top of that, right? So there's some software architecture decisions that are made there that
Yeah.
they're challenging, right? Like I'm not gonna
Yeah.
it's easy to talk about them, right? But it's doing that. It's not. It's takes iterations. I'd say.
The other interesting thing that I saw you do, and I might be butchering this because I'm not an FPGA programmer, but there was a way that you were taking the FPGA reference and it includes the bit file reference, like includes all of the inputs and outputs. And you're able to like segregate that. So like a particular class or driver could just use bits and pieces of it and you could have multiple classes. Is that, am I describing that correctly?
So right. So when you in LabVIEW FPGA, when you open the reference to the bit file, right?
Mhm.
So now you're communicating with that card with that bit file. The reference is the casting of that reference has FIFOs, registers, like there's a whole bunch of IRQs, like there's a whole bunch of things that are part of that. And if you go into a sub VI and you just want to write a single register, you don't need to have all of those things in that reference. You just need the one thing that you're writing to. And I haven't seen a lot of cases like this, but you could have, let's say you were making like a whole family of like FPGA cards or bit files. So you could have some that have like common code that they all support. So
Mhm.
like this API that like DACMX is a perfect example where they have the DACMX. I mean, it's good to look at those things because NI's thought that through in that case. And so you have like the digital cards or the multifunction cards or the analog cards or the analog input cards. They all work on the same reference, but then behind the scenes, it figures out, oh, we're working with a really specific card that has this ability. And then you're able to do that. So like the LabVIEW FPGA part is really not too different in that sense. You
Okay.
could
So,
make it you
yeah.
could make it access specific capabilities.
So that's more like, I don't know, maybe like, I don't know, like interface segregation or something, right? Where like you only get the interface of the things that you need and you're not like
Yeah.
troubled by
Well,
other things. And then it lets you swap things out too, I would imagine, right?
probability. It's also like those tests, like that code, less code changes, right? So if I just need to go and change certain parts of the code, certain parts of the bit file, like on the FPGA, if I'm changing certain aspects of it, if that impacts a smaller portion of the API, then it's easier to do like your regression, your testing. It's not really regression, like whatever you need to retest for that change. Less things have changed. In theory, less things have changed. You probably need to run all of them, but there could be some benefits gained there
Yeah.
in terms of that segmenting.
Yeah. No, that's really cool. Yeah. So I mean, just in general, like on that project, like I just the the whole workflow I think worked really well. Just like and part of the problem was I don't think they had a workflow to begin with. I think was kind of part of the problem. Like they were just like very much code and fix, I would call it, right? Like you write the code, you kind of run it, it looks right or it doesn't. If it doesn't, then you go fix something and then run it, which is actually kind of weird, right? Because I feel like code and fix coders still do that iterative thing, but like they just like I don't know what it is, but
Well, with the FPGA, you have a lot more things going on, right? Because in that project, we had someone that was working on Verilog, and he
Mhm.
had to verify certain things and checks things out. And if we couldn't really debug his stuff inside a LabVIEW FPGA. Like sometimes we'd find like a problem, but then he'd have to go and fix it and verify it on his end, right? So there's really, I think with an FPGA card, like the complexity, it looks like it's just one card, in quotes, like one card or two cards, but there's a lot more complexity going on that again, I keep using the DAC example. If it was like a DAC card, we wouldn't think that that complexity is way less.
yeah.
So it has to be appreciated that there's more that has to be, you have to be really careful. The quote unquote like small change is uh is a big one.
Yeah. So speaking of complexity, reading your book, one of the things I took away from your book is that there's lots of ways to interact with the FPGA and lots of ways to pass data back and forth. Do you have
Yeah.
any tips or tricks or hints on like what you should consider when you're picking one way over another?
You're saying like from the host computer into the
Yeah,
FPGA.
yeah, like DMA, FIFOs, you could send data
Yeah.
controls. Like I'm sure there's probably other ways that I'm missing.
Yep. So it's right. So you got DMA FIFOs. Like there's five FPGAs in general deal with like FIFOs, right? Like you have to like it's almost like a queue in
Okay.
LabVIEW software. So we have a DMA FIFO is a FIFO that goes from the host to the FPGA or from the FPGA to the host. So it's unidirectional. And then the other thing that they have is they actually have like when you make a LabVIEW FPGA VI, all the controls and indicators on that front panel immediately become when you compile it, they become registers.
Okay, registers, that's it. Okay.
So the registers are kind of like static, like they're almost like variables. Like there's no buffering, and like there's no streaming capability that they have. So if I'm just setting like uh, coefficients or things that are not going to change, like while the test is running, I would probably use those types of interfaces. But if I have data that I want to stream into the FPGA and stream the data back, like if I've got like sensor data that's coming in and I need to stream that back and I need everything, I need it to be lossless. I would use a FIFO for that.
Okay. Yeah, so that's kind of just similar considerations to like regular LabVIEW communication, right? Does
It's
it be
it's
lost?
it's really, I mean, it's communication, really, right? In that sense, it's
Yeah.
really really similar.
Okay.
Yeah.
Cool. And then like FPGA is like communicating in between loops. Like I know in RT there's a lot of considerations about like if this is your like timing loop, right? You want to be very careful about things like introduce jitter and stuff. Are there considerations like that for FPGAs?
So with FPGAs, jitter is if you're if you're using a single cycle time loop. That's a type of loop where you're telling it that if everything in here can't run at the specified clock rate, it will not pass the compile.
Yeah, yeah.
So you could add things, whatever you add into that, if it's going to break it, you won't get a compile, right?
Okay.
That's like that'll catch you like no matter what.
Yeah, so there is no jitter once it compiles because it won't compile if it
On FPGAs, the jitter, the in quotes, it is jitter. It's not in quotes. It is literal jitter. Jitter in hardware is comes from environmental conditions like temperature.
Oh, okay.
Literally, like the temperature changes, it's going to run that. Everything has jitter. It's just that it's a much lower jitter and it's more bounded than it is in software.
Okay. Yeah, because like software, right? Like RT loop or something, if you're like allocating an array or resizing an array or string stuff that like
Yeah,
is unpredictable. Yeah.
which on an FPGA you can't allocate an array, right? Like your arrays are all fixed
Fixed
at compile
size.
time, or we don't have strings. Well, we do have U8s, right? A U8 is how we handle strings,
Like a byte array, yeah. And it's a fixed size array, yeah.
and it is fixed. I think the other thing is that the way we process data on an FPGA is very different than in software. Like I like to think of processing data in an FPGA almost like an assembly line,
Mhm.
where like data when data comes in, like on a certain clock cycle, a sample comes in from a sensor. You have to immediately act on that data. You don't buffer it up like a million of them or a billion of them that you as you could in software, right? You could collect a bunch of data in
Mhm.
software in an FPGA. Like once data comes in, you want to think of like what can I do to that data immediately. So you're not really holding on to data for too long. You're immediately acting on it, or you're. I mean, sometimes you do need to collect things. Maybe you're doing like a moving average or a
Yeah,
running average.
this is
You
where
do
you
need
do
to
the
collect.
point by point calculations, right?
Say it again.
The point by point calculations, right? Where it's
Right.
just here's the new point, add it to yeah, okay.
Whatever it is, yeah, whatever it is we need to do to it, or filters maybe, like, but whatever it is, it really is point by point. You need to act on it as it comes in.
And then if you need to take longer than that, then you do the pipelining thing to like push it off to the next iteration. Is that kind of the
Pipelining comes into play. So we so pipelining will add latency because that means that you're adding extra clock cycles to do something.
yeah.
But the reason we'll pipeline is because we're not able to meet the timing that's required typically. So like if I write some code and I wanted to run it like say 100 megahertz, but it doesn't compile at that rate. One of the tools that I have that an FPGA developer has, like that we can use, is pipelining. So we'll essentially like break up that calculation either in chunks, like these two multiplies, I'll just pipeline them, or the FPGA tool itself can actually pipeline the multiply itself internally.
Okay.
It's
So yeah, so like the data
kind of
comes
like it's kind of like an assembly line, really.
delayed a little bit, but they both are moving at the same rate, right? If I understand that correctly.
Well,
Right? Like
think of
clock,
a
this is getting
yeah.
updated every 100 milliseconds. This input's getting read every 100 milliseconds, but there's a delay between the input and the corresponding output, right? Am I
So
thinking
let's
about
think
that?
of an assembly line, right? If a car goes on, like I have a chassis with no things on the car, it goes into an assembly line, right? We're going to put a few things on there, and then it goes to the next stage, and then the next stage. That's pipelining.
Yeah, yeah. But like I guess the output of the cars is now X number of cars per minute, right? Like it's going out, but like the time from when it goes into comes out is where
That's
there's
your
a
latency.
yeah,
So,
that's related.
so right. So it's I use this metaphor a lot in the in training or talking to people about it. Um, let's say the factory is empty. Nothing is in the assembly line. I put a car in there, and then how long does it take for it to get out of the like to be
Exactly. Yeah.
built? That's your latency.
Hmm.
So let's say it's like in our case, let's say it's microseconds or milliseconds. With them, it may take like a day or I don't know how long. I don't know automotive, right? But it takes a certain amount of time. But once that pipeline is full,
They can
we're
pump.
getting a car every 6 minutes or every hour or whatever. You know, that depends on their resources, right? Like they can add more links to that. They can add more stages to that pipeline and increase throughput. But the cost is latency, right? So whenever I do add pipelining, right? So if I can compile it in the FPGA world, I can compile at a certain rate.
Mhm.
So I add latency. I add pipelining. Now that adds latency, but we assume that the latency is acceptable in that case. The
Yeah.
amount of latency that we're adding, because you may need to respond to it. I mean, if you think of a more relatable case where latency is a problem, is a self-driving car. Not that
Right.
I've worked on that, right? But you
Something
need to
run
respond
respond in X number of seconds or something or milliseconds.
microseconds or milliseconds, whatever that is, right? Like that response is safety critical, right? Like sometimes there's performance cases, right? Like with a radar system or with some kind of an RF system, the response has to happen. Like if it doesn't happen within a certain time period, the other side that's like sending you the signal may think that you're not functioning like functionally. It's expecting that latency.
Yeah, okay.
So it's
Yeah, those are all interesting things that like you writing Windows programs, you don't necessarily always think in those terms because Windows is very non-deterministic.
Yeah.
Yeah.
Yeah, I mean, we're certainly we're thinking of performance when we're doing Windows. I think the performance just gets stated in different terms, right? Like
Yeah.
in Windows, if you have a program that's not responsive or it's really slow, right? The user experience is really poor. That's sort of a latency issue, right? Like I
Yeah.
clicked on something and then like I got nothing.
Yeah. And then all of a sudden it spits it out. Yeah. So we still do care. It's just different types of concerns and
It's phrased
situations.
differently, I think. It's certainly it's I know it's easy to say kind of that, the FPGA really cares about more things, but we're all dealing with performance, right? Like there's always some kind of performance that we're held to.
Yeah. And then talking about performance on FPGA, the other thing is the fixed point math. How long, how hard is that to wrap your head around? How long did that take you to, or is that pretty easy?
um, I'll tell you a story on that. So the first time we started to use fixed point math, back with the Wall Street FPGA days, um, we were looking for like Monte Carlo simulations that were simpler than options cut pricing. So there is a Monte Carlo simulation called Buffon's Needle, and it's a way of it's named after a physicist or a scientist, and it's a Monte Carlo simulation for estimating pi. And
Okay.
since we know what pi is, right, it's in quotes like an easy one to kind of learn.
Yeah, and
And
you could
so
test yourself by how close you get. Yeah.
it's easy to test, right? Like we know the answer, right? And to 10 digits or whatever. So we first wrote it, and then we wrote the algorithm, right? Like it's a pretty simple algorithm. There's like a divide, there's a multiply. I forget the formula for it, but it's a relative. If you look up Buffon's needle, it's pretty simple. So we the first time we ran it, we got 2.80000, which we know is wrong. But then when we probed the LabVIEW FPGA code, we saw that somewhere it was like saturating.
Okay.
Like we corrected that. We had to set the bits. So like for floating point math, the point floats, right? It'll go to fit the range of the value that you're sending in.
Hmm.
With fixed point, it's fixed. So if I have like a value of 500 and I want to put it into a fixed point number that can only go up to 100 to one, it's going to saturate it,
Yeah,
right?
yeah.
It doesn't know what to do with those bits.
Hmm.
We made that correction. We ran it again. We got 3.10000. So we know that's still closer to pi, but not pi.
Yeah.
And then we found where the last error was, and then we saw that we were able to get pi. So fixed point math really what's really needed is it's actually the technique is called a range analysis. So in other words, like you're supposed to look at each of the math stages, each of the computing stages of your FPGA, and you have to ask yourself like, what's the range of the data that's going to be here? And then what's the range of the data that's going to be here? And you kind of check all those points. You can simulate it. That's the beauty of it. That's the plug for, not that it has to be plugged, right? But simulation is supposed to help you not have to wait for long compiles to
Because
get the
that's
fixed
just a
point
lot of
math.
problem and you can catch that. Yeah.
That's right. I mean, fixed point is even supported in LabVIEW for Windows, right? Not that we would use it there, but what I'm saying is that you can actually just I don't think even need to have LabVIEW FPGA installed. You could just go in and just choose a data type to be FXP, and you can kind of click around and see kind of how that works.
On Windows, that would probably actually slow you down, wouldn't it? Because it's still reading and writing like 64, 32-bit registers no matter what you do.
That's right. That's right. Whereas on the FPGA, it actually becomes a strength because FPGAs don't have data types.
Yeah, so they're not always allocating a 32-bit chunk. They're allocating whatever you tell it to allocate.
It's bits, or it depends on like the actual resource. Like if
Yeah,
you're using a DSP that's like a certain number of bits,
that
it's
probably requires, yeah.
a different thing. In fact, I think it's Microsoft. There's different like companies that have talked about it. But I think like with some of the newer algorithms, like the machine learning algorithms, they need floating point, but like 11 bits.
Ah,
So on the FPGA, you can actually make your own multiply functions and add function and math functions that are just it's a different data type
yeah,
that doesn't exist, right? There's nothing for that, but on the FPGA, you could create that.
yeah. Cool. So you mentioned Monte Carlo simulation a couple times, and I'm not sure that everybody knows what that is, and I'm not entirely sure I do. So let me tell me if my explanation is correct, but basically it's kind of like an iterative thing where you're like getting closer and closer to the solution, and you're
Yeah,
basically guessing every time, and then you look and then you do another guess to kind of get you closer. Is that basically it?
Yeah, you have a randomizer. Like in LabVIEW FPGA, we use like a noise function to generate that random value, and that's how you keep putting a random value in there. And the thinking is that it's a way of figuring out, like it's an optimization, right? To figure out like a number instead of doing it incrementally or mathematically. The thinking is that you could put random numbers in there
Yeah,
to get
like
to.
this method is like basically you step towards the answer, right? And this is just you randomly pick and then
Yeah,
is it like divided in half? Like wherever you pick, is it like two halves? Is it kind of like a binary tree type thing? Like you pick and or does it just I don't
I don't think it does a binary. There could be variations, but it could be, but I'm not.
well, yeah, that's outside my thing. I know when I worked at Westinghouse, they were doing a lot of Monte Carlo stuff. They were doing computational fluid dynamics. So they were trying to model
Yeah,
the
yeah.
way that fluids flow around a nuclear reactor. And yeah, there's a lot of variables that go into that, apparently. And it's kind of a chaotic system. So it's
Right.
one of those things where like the
That's how you
start.
want to model chaos, right? Is with the random numbers.
Yeah, exactly. Yeah, because like the starting point, like if it's a few degrees off or like something's a little slightly different, then it goes off to whatever. So it's very interesting stuff. But they would run simulations, kind of like the FPGA stuff, where it would take a long time. They would run those things and they would just like walk away for like a few days or a week and come back. And so yeah,
I would say that in our experience, I mentioned earlier that sometimes people would compare, put FPGAs and GPUs kind of in the same boat because they're a form of hardware acceleration, right? Like it's not a CPU, so it's something that can, accelerate an algorithm. And quite frankly, with Wall Street FPGA, we backed off of the Monte Carlo case study was useful to demonstrate certain things and demonstrate that LabVIEW FPGA could make an efficient FPGA. But because that can be done by GPUs, it was less competitive. Whereas like the network access and some of the other parts, like with any tool, you want to focus it in on like where it's most competitive or most efficient. And so that part, because it's being done, and even these days, right? People use GPUs for a lot of things, and they don't have the compile time. The skill set is, you don't need to have the hardware knowledge that an FPGA developer needs to have. So and a lot of those simulations can be done. They're not really latency sensitive, right? Like you just need to take a models and, like I said, random data and just throw it at it and just run those models. GPUs are just as can be uh, they can be very competitive for that,
yeah, I
maybe
think this
be
is a
better,
great
right?
topic to wrap it up. So can you like summarize the difference between FPGAs and GPUs like in a few sentences? Like or is that kind of what you just did, I guess, and I'd like, or is there more to it?
Um, I guess they definitely have overlap, right? I mean, if I want to run something, um, I guess the difference is that a a GPU typically like you can't control the type of I/O it's going to connect to, right? It's kind of like this processor. It's good at doing floating point, whereas an FPGA may not be as good as doing floating point. Like a GPU in a sense, it's really made for like processing like arrays and matrices, right? So it's actually for a specific type of thing, whereas an FPGA is more customizable. Now, if you're customizing it to do what a GPU does, that's not efficient, right? Because you could just use that. But I would say that one thing we talk about data centers, one thing that FPGAs are, there's a lot of costs, right? Like to all these things. One of the things, cost of development is one thing, but the other thing that's becoming an issue is, and it's been documented, is that GPUs are more power hungry. Like per calculation, they use more power than the equivalent FPGA would because we can control that a lot more. With the GPU, you're just sending it more, you're sending it instructions. You're not really managing power. So as things start to scale and there's like larger amounts of computations, I mean that exists already, right? Like all these data centers that we have out there. The appeal of FPGAs is to use, there is a power efficiency that they get, but that's not the only reason that one uses it. So it's a I would tell you that both the FPGA companies make papers that talk about why they're better than GPUs, and the GPU companies make the same thing where they're better, right? Like so, it's hard to really just summarize it, but I mean, I've given a couple of data points there.
So it basically just comes down to your use case more than anything.
It does. It does. I mean, for example, if I was doing something where I'm just collecting a bunch of data and I need to run a bunch of models on it, GPU could be a good, maybe good enough for that. But if I need to like receive data, make a decision on it, and then respond back within microseconds, you probably can't do that with a GPU.
Cool. No, that was I think that's a great thing to wrap things up with. Do you have anything else that we didn't? I feel like we talked about a heck of a lot of stuff, we covered a broad range. But is there anything we missed that you wanted to make sure to mention?
I, you know, yeah, I think we covered the things that it would be a rehash, I think, of some of the other things, but
Great.
it
Cool.
was fun to talk about this.
Yeah, no, thank you very much, Terry. That's it for today's episode of the LabVIEW Experiment. Thanks for listening. If you have any comments or questions, head over to thelabviewexperiment.com and drop me a note. And don't forget to subscribe to the podcast and follow us on Twitter and Instagram at the LV Experiment.